Good morning, everybody. Welcome to Honors Chemistry. Today is Wednesday, April 29th, and let's see, 2020, I guess, is the year. It's still 2020. My gosh. Anyway, welcome to chemistry. Let's go ahead and take a peek at the agenda for today, and we'll go ahead and get started. So here we go. Yesterday, you guys watched a series of videos for me. I want to talk a little bit about some of the information I hoped you gained from that. And today we are going to start with molecule of the week. I'll review some information about electrolytes that you should have gotten from yesterday. And then let's see, I'm going to teach you molarity and molarity by dilution. And then, gosh, unfortunately, we are going to miss out on one of the most important labs that we do all year. And that's the preparing solutions and dilutions lab. So I'm going to get you ready for that. I'd like you to, you're not going to be able to do it at home. Actually, you could probably do it at home if you wanted to, but I'm at least going to have you do the calculations because it's a really important skill in being able to make solutions in the lab and dilute them down. So I'm going to ask that you guys actually just do the calculations associated with the lab and turn it into me on Google Classroom tomorrow. I created that assignment for you in Google Classroom. And then I put some exam review up for you. And then Friday morning, we'll meet up and I'm not even going to record that session on Friday morning. I'll just answer any questions that you have. And then we will have an exam ready for you on Friday. So I'll answer any questions that you have on Friday. And then after I'm done with my question and answer session, I'll go ahead and post the test for you. And at some point on Friday, if you would please go ahead and take that exam, that would be great. It would be in Google, it'll be a Google form in Google Classroom. So, and that exam will cover intermolecular forces and solutions and basically states of matter, like the difference between solids, liquids, and gases, and whatnot. So let me go ahead and show you where you can find some things on Google Classroom. So let's see, we are going to be doing these notes today. So if you would please make sure that you have these available to you, either printed or just have them accessible on your computer. We're going to go through those in a few minutes. This is a worksheet I'd like you to try for homework tonight, and I've included the answer key here. The answers are not worked out, but the answers are there. So if you have any questions about how to work them out, please don't hesitate to shoot me an email. But you should be able to do these 10 problems after we get you those notes today. Here's an exam review for you, just a little extra practice before your test on Friday. And you'll notice there's something here. Where is it? Oh, it didn't come out right. Oh, darn it. You are not going to be responsible for 11 part C. I thought I had crossed it out, but actually, I'll upload a different exam review. There's going to be two parts of this that are crossed out. The molality, you'll notice something here in 11C. I'm going to cross this out, and I'm also going to cross out another place where molality is brought up in number 9. This term here, molality, is not something I'm covering this year. It's a concentration it's a way of measuring concentration, but to be honest with you, I used to teach it. I don't teach it anymore because it's no longer on the AP exam. And so I'm not going to worry about teaching you how to do it because I don't teach it to AP either. So, so if you want, just hold off on this review for just a few minutes. As a matter of fact, I'll even take it down right now while we're thinking about it. Let's see. I'll take that one down because I will cross out the ones you're not responsible for so you don't get confused while you're doing that. Just write myself a note to do that. Okay, so that's there. So you've got, let's see. Okay. Oh my gosh, what's going on here? Go back. There we go. Okay, so the Molarity notes we're going to be doing today, this worksheet is something you can work on for homework tonight for some extra practice. That exam review you can work on tomorrow night or whenever you have some time, sometime before Friday, so you can ask me questions. And then this lab, I'd like you can try it in your house if you want to tomorrow, but I'm going to take you through at least the pre-lab for that by the end of the period today. And I'd like you to do the calculations associated with it and turn it into me on Google Classroom by Friday morning. I think I put, by 8 a.m. on Friday morning. So that would be your lab for class tomorrow, okay? So those last 4 things that I've uploaded into the classroom are going to take us through the remainder of the week, and then we'll have a test, okay? So let's go ahead and get started here with molecule of the week. So there we go. Okay, molecule of the week this week is one that is a new one for me, actually, heparin. I was talking to my husband when he got home from work the other day, and I said to him, honey, I really want to do a molecule of the week that is meaningful to what we're all facing right now and what the medical world is using to treat patients that have COVID-19. I said, what are you guys using on those patients? And he said, oh, heparin. So I decided to make heparin into my molecule of the week. Heparin is the most widely used anticoagulant in the medical setting. It's a blood thinner, okay? Anticoagulant means it keeps your blood from clotting. So it prevents what we call thrombosis, and thrombosis is just the fancy medical word for clotting. It was discovered in 1916, and it was originally harvested from dog livers, hence the name or the prefix hepa in the word, because hepatic refers to liver. So heparin is isolated from the liver, and it's a naturally occurring polysaccharide. So a polysaccharide is a type of sugar or carbohydrate, and it has a repeating subunit. So this is what this repeating subunit is, just basically these 2 ring structures that are repeating. And that's what makes the polysaccharide. They all link together. It's administered to patients to prevent strokes. Strokes are caused by a blood clot in the brain. Heart attacks, that would be caused by a blood clot near the heart. And then pulmonary embolism would be a blood clot that is in your respiratory tract, in your lungs. And that seems to be what's happening a lot with these patients that are coming in with COVID-19. They're getting these pulmonary embolisms. They're getting blood clots in their lungs because the coronavirus is attacking the respiratory tract, the lungs. And so they're trying to treat these patients with heparin to avoid getting those pulmonary embolisms. It's a potential therapeutic drug that's currently used to treat the thrombotic effects of COVID-19. Thrombotic meaning blood clotting effects of that coronavirus. Side effects are excessive bleeding, right? So if somebody's taking heparin, if they're on blood thinners and they do something as simple as bump into a piece of furniture, their body's not going to be able to clot the blood quite as easily. So they could get excessive bleeding, or if they cut themselves in the kitchen while they're preparing a dinner, they might bleed. They wouldn't be able to form a scab. And so that bleeding and bruising is as a side effect of taking heparin. Another side effect would be a fun word to say. This is called thrombocytopenia. Thrombocytopenia. I had to include that word here because it's such a fun one to say. Thrombocytopenia is a fancy way of saying a reduced platelet count. So it would be harder for those patients to clot their blood because they'd have less platelets. Mosquitoes and leeches have natural anticoagulants in their saliva. It's because they're blood-sucking creatures. So if a leech grabs onto you, they want that continuous flow of blood. So they actually have natural anticoagulants in their saliva that keeps your blood from clotting so they can continuously get that flow of blood. And same with mosquitoes. So that's an evolutionary advantage where we see anticoagulants in blood-sucking organisms. And they do use those anticoagulants in nature as a model for potential drugs that when they're designing drugs. And then if you just look at the structure of this heparin real quick, I would like you to just think, do you think that this would be soluble in water? Just think for a moment about some of those videos that you watched recently, some of the things we've been talking about over the last couple of weeks. Looking at this molecule, do you think it would be soluble in water? And hopefully you're thinking, yeah, it would be soluble in water because of these charged side chains, right? So I've got negative charges on these side chains here, and those negative charges would be able to form ion dipoles with the water molecule, just like salt can, right? When you dissolve salt in water. So you also have these OH groups here. Those OH groups are polar, so they could form hydrogen bonds with water molecules surrounding it. So heparin is indeed a water-soluble compound, okay? And then this would be the space-filling model of what it looks like. All right, so there's your molecule of the week, heparin. Okay, also, before I forget, I wanna point out that on your agenda, back over here, I posted an extra credit assignment, if you will, or opportunity for our Instagram account. I love seeing your faces. It brings a lot of joy to my days to see pictures of you all online or on Instagram. And so after last week, we did the tree hugging Instagram extra credit. Today, or I'm sorry, this week, I'd like you to post a photo of yourself that represents how chemistry impacts your life in a positive way. And I've already seen a couple of you have posted pictures of yourself. I got to see Lauren making brownies, made my mouth water. I wish I could have some brownies. That sounds good. And Ozan posted a picture of himself in lab as well. So I just want to see a photo of yourself and tell me how chemistry is a part of your world. Okay. And don't forget to follow at least 20 or 30 other people. And when somebody requests to follow you, follow them back, and then they'll just bring a little bit more joy and happiness to our lives. All right. So that's that. Okay, next up, I want to talk a little bit about some of these videos that you watched yesterday. The Solutions Lab at Home, you know, that wasn't as good as I wanted it to be, but what I really hoped you would get out of that was the idea of just what some of that glassware looks like, okay, what a volumetric flask looks like. The volumetric flask is perhaps my favorite piece of glassware, and it is what we use to make solutions. So you saw volumetric flasks in that video. Water, the Great Dissolver, that was a video that's kind of old school. I bet you've picked up on that. I've been using that one for years, but it's got really good visuals in it. And then this other video on electrolytes was something I wanted to talk about too. There's one of my favorite demos to do for you is called the electrolyte demo, where we test a lot of different solutions with a conductivity tester. And essentially, if the solution conducts electricity, then the light bulb lights up. And so I just wanted to show you guys what this might look like digitally, I guess, because I don't have my apparatus with me. But if we have a solution that's just pure water, now water does something called self-ionize. It does form some ions. So in this container of water, it's not pure H2O. Most of it is H2O, but some of it will self-ionize, and the hydrogen will go from one water molecule to another, forming these two molecules. And so if I put these two electrodes down, you can see that there might be a little bit of conductivity. But if I replace that, pure water doesn't really conduct electricity very well. But if I put a strong acid in there where there's a lot of ions, okay, where these positive and negative charges are there, you can see, wow, that light bulb lights up a lot. That's what we would call an electrolyte. Electrolyte is something that conducts electricity. So in other words, if the current is completed between these positive and negative electrodes here, then the light bulb lights up. And what you need to complete that current is charges, flowing charges. Okay, so if I have these ions in here, these positive and negative ions, those are flowing because they're in the liquid phase, right? And so if it completes this circuit and makes the light bulb light up. You can see if I put a weak acid in there, and you guys don't know acid-base chemistry yet, but weak acid has some ions in it, not quite as much as a strong acid does. You can see it doesn't light the light bulb up quite as strongly. We would call this a weak electrolyte because it's a dim light. So strong electrolyte is bright because there's lots and lots of flowing charges. A weak electrolyte would be a dimmer one. And then we'd see also, we can see the strong base is also a strong electrolyte. There's lots and lots of ions floating around in there. As long as there's ions to complete the circuit, as long as there's flowing charges, it'll conduct electricity. And then a weak base has some ions, and so you can see that it is a weak electrolyte. And then water is really, really dim here. You can see that there's almost no ions, and therefore it doesn't light very much at all. And so one of the things that you saw in this video, this first video yesterday, was Gatorade. They like to talk about Gatorade as being an electrolyte. And you might wonder, why would they call an electrolyte? Why would someone advertise electrolytes? Why would you want to drink an electrolyte? Okay, and so the reason why, and we actually would test Gatorade. Indeed, Gatorade is an electrolyte. If you put Gatorade with these two electrodes, it would actually light up the light bulb. So what they claim about Gatorade is indeed true. It's an electrolyte. Now, why would you want to drink electrolytes? Well, if you look at the side of a Gatorade, which I can't think if I have any in my house right now. Oh, wow. If you look at the ingredients of Gatorade, you would see that it has some salts in it, some charges. Let's see if I can actually Google search the Gatorade ingredient. A little bit more. Just taking my word for it. Here we go. Blue Gatorade. Oh, here's the red Gatorade. Okay, so if we look here at the ingredients of Gatorade, you'll see it's water, sugar, dextrose, citric acid, there's salt, there's sodium citrate, monopotassium phosphate, food starch, natural flavors, red 40 glycerol. Okay, there's and then some color in there. So we do see some charged particles in there. That's sodium, that potassium. And those are what's making Gatorade an electrolyte, because they're charged particles that are flowing within that liquid. So indeed, it would conduct electricity. Now, why would you want to drink that? Well, because when you're exercising and you're sweating, right, the ions that are inside your body dissolve in your sweat. And so you actually sweat out some of these potassium and sodium ions that are in your body. And you need those ions in order for your body to function in its maximum capacity when you're doing athletics. So for example, when you're running, right, you're relying on your muscular system. Your muscular system relies on calcium ions to function. Okay, so you need those ions for your muscles to be able to contract and relax. Your nervous system is also really important if you're playing sports or exercising, right? You have to be able to catch that ball or avoid the defender or whatever, right? So you've got to be able to see. You're going to need to rely on your nervous system and so that you can react. And your nervous system relies on sodium ions and potassium ions and chloride ions. And so all these ions are indeed electrolytes that they put inside of some of these sport drinks, and they claim electrolytes, whereas the majority of the population doesn't know what an electrolyte is. In chemistry, an electrolyte is any solution that conducts electricity. And so the reason why it conducts electricity is the fact that there's ions that are present in solution. So, okay, so that's so what they claim to be true is indeed true. Okay, so next up, let's see, we've talked a little bit about electrolytes. You can see they conduct electricity. Next, let's take a look at the notes, molarity and molarity by dilution notes. So once again, those are in the classroom. So if you go over to our classwork section and you pull up these molarity and concentration notes, this is what we're going to do together right now. And I'm going to do my best to annotate directly on here, so we'll see how well this goes. So concentrations of solutions. Usually I would have you guys put this into your brain books. If you want to write it into your brain books, you can. This is perhaps the most important skill I can teach you as a chemist, is how to make solutions. It's one of the things that I do most often, okay, in preparation for labs for you all. I have to make solutions, and those solutions have to be of certain concentrations. So this skill is one that I'm just really frustrated that we're not together in lab, so I can't actually teach you how to make solutions with the proper glassware and whatnot. But it's one of those things that Miss Cunningham does all the time. I do it all the time. If you were to go off to college and you want to go work in a professor's laboratory, this is what you want to do. You want to be able to prove yourself as a good lab assistant. And what you say is, I know how to make solutions of different concentrations, and then they're going to hire you on the spot. Okay, because every lab needs somebody who knows how to make solutions properly. So all your friends can go off and work at Starbucks when you go to college, but you guys are going to go work for a professor as a lab assistant, and you're going to make better money than your friend at Starbucks. And then you're going to get a letter of recommendation from that professor for grad school, and you'll be well on your way. So this is perhaps one of the most important skills I can teach you, is how to make solutions. Okay. So concentration is just a way of measuring the amount of solute in a given amount of solvent. Okay, so the way I remember it is solute is what's being dissolved, and then solvent is what's doing the dissolving. So usually solute is present in smaller amounts, and the way I remember it is that solute is a smaller word, right? There's only 6 letters, and whereas solvent has 7 letters. So the smaller word is present in smaller amounts. And so we just need to understand first the difference between dilute and concentrated. Dilute means that there's a lot of solvent and very little solute. So let's see if I could draw this for you. It would be something like this. Okay, where I just have a little bit. Goodness, that doesn't look very good. That's not what I want. Hold on, let's try this again. I clear everything. All right, draw, I want this. Here we go. So if I have dilute, I would have just a few little bits of solute in my solution. We can think of this as, there's my solvent, okay, just a little bit of solute. So if this would be like Kool-Aid, you'd have a little bit of Kool-Aid and a whole lot of water, right? Versus concentrated would be a lot more solute in there. So draw a whole lot of little dots in here. And ideally these would all be the same size, but I'm doing the best with what I have here. I'm just trying to show you that there's a lot more solute here. Whoa, it's a lot more concentrated. Okay. There's a whole bunch dissolved. So if you had really concentrated Kool-Aid, you would have it would be really, really sweet, right? Lots of sugar in it, and very little water. Okay, so this is what a concentrated solution might look like. Not perfect, but you get the idea, hopefully. Okay, there's a lot more stuff in it. Okay, now water is a really good solvent. Almost always the solvent is water, unless otherwise stated. You can assume that the solvent is water. And you watched that video yesterday, the kind of cheesy old school video where they call it water is the great dissolver. And the reason why water is so good at dissolving stuff is because it's polar. And there's this idea of like dissolves like. So water can dissolve anything that's polar like itself, or it can dissolve any ionic soluble substance. And you guys already memorized your solubility rules, so you know what kind of ionic substances will dissolve in water. Okay, so there's dilute versus concentrated. Okay, moving on to molarity. Okay, so the most common way of measuring concentrations is what we call molarity. And molarity is abbreviated with this capital M, and it stands for the number of moles of solute per liter of solution. So the units are moles per liter. Okay, now notice it's moles of solute per liter of solution, and solution is solute plus solvent, right? So it's the two together, right? Solute plus solvent makes solution. So if I were to say I want, I would say 1 molar NaOH, 1 molar sodium hydroxide, you might write or label this solution 1 capital M NaOH, okay? And that would mean that I put 1 mole of sodium hydroxide for every liter of solution. I fill it all the way up to make 1 liter of solution. Okay, and so when we label a solution in the lab, you would put, I would probably write something like this, 1 molar NaOH, and then I would put the date that I made it, and then I would also put my initials on it like this. Okay, so that would be on a typical label that in my stock room, okay? And then you know when the substance was made, and you got to label the concentration and what's in there. Otherwise, most substances just look like water. Okay, so let's do an example. It says you have 3.5 liters of a solution that contains 90 grams of sodium chloride. What is the molarity of the solution? Okay, so let's see here. The first thing, if I know that I need moles per liter, when in doubt in chemistry, convert to moles. So I'm going to take this 90 grams of sodium chloride and convert it into moles. So let's start with that. So I have 90 grams of sodium chloride. Let's go ahead and say the 90 grams, 0. This by the, I'll end up dividing it by the 1 mole of sodium chloride for every 58.44 grams. That's the molar mass of sodium. That'll give me 5 moles of sodium chloride. Okay. So 90 grams of sodium chloride is 1.54 moles. And then I can just say, all right, moles of sodium chloride. And I divide that by the volume of my solution. Then I end up with the molarity, which is going to be rounded to 2 sig figs because of the 3.5 keeps that to 2 sig figs. So it would be 0.44. So that's what I would, I'd go over to my scale, I'd measure out 90 grams of sodium chloride, I would fill it to 3.5 liters of solution, and then this is what I would put on the label. I would label it 0.44 molar sodium chloride, okay? And so that's it, pretty simple, pretty straightforward, okay? All right, next, let's see, let's try another one. Let's say you have 0.8 liters of a 0.5 molar hydrochloric acid solution. How many moles of hydrochloric acid does this solution contain? So once again, this molarity is moles per liter. So let's start by just writing that. Remember, molarity equal to moles of solute liter solution. Solution is solute plus solvent. It's the total volume together, okay? So if I just plug and chug here, I can say, all right, well, 0.5 is my molarity, and that's going to be equal to some X number of moles divided by 0.8 liters. I've got, this is my molarity, the volume is 0.8, so all I have to do is multiply both sides by 0.8, and we'll end up with X is equal to 0.4 that are present inside that volume of a solution of this concentration. Okay, and so there's my answer right there. There we go. Okay, so once again, pretty straightforward, just a simple plug and chug most of the time. Okay, all right, let's try the next one. Next one is parts per million. Now this one came up the other day when we were looking at the water quality of Manhattan Beach, and you guys looked over the water quality report for Manhattan Beach. And remember, we said parts per million is the way that they measure concentrations a lot in environmental chemistry. It means milligrams of solute per liter of solvent, or if you want to think of it in terms of mass instead, it's milligrams of solute per kilogram of solvent. And the reason why is because usually the solvent is water, and water has a mass of 1 gram per milliliter or 1 kilogram per liter. So a liter of water and a kilogram of water are the same because water has a density of 1 gram per mil. Okay, so anyway, the one that I like to use to explain parts per million is kind of fun, the Dead Sea. I don't know if any of you have ever visited the Dead Sea. I never have, but usually I've had 1 or 2 students who've been there. And if you get to go visit the Dead Sea, they often let you swim in it. But what people have told me is that you can't actually swim in the Dead Sea. If you tried to get underwater and swim around, it would be very, very difficult because the Dead Sea is really concentrated with salt. As a matter of fact, they call it the Dead Sea because nothing can live there because it's so salty. It's such a salty solution that you actually just bob up and down. You don't even have to try to float in the Dead Sea. You just automatically float because it's such a concentrated body of water that you just float. You can't sink if you tried. So if you've ever been to the Dead Sea, you've bobbed in the Dead Sea. Anyway, Dead Sea is the saltiest sea in the world. It contains 332 grams of salt per 1,000 grams of water. What's the concentration in parts per million? So this one's, again, pretty simple. Remember, we need milligrams of solute per liter or per kilogram of solvent. Okay, so 332 grams, you can convert that to milligrams. That's going to be 332,000 milligrams divided by the kilograms of solvent. Kilograms of solvent, well, let's see, my solvent in this case is water. I have 1,000 grams, so that's equivalent to, so 332,000 milligrams per kilogram is the same as 32,000 per million. Okay, so here our answer is D. 332,000 parts per million is the concentration of the Dead Sea. Okay. The main difference here is that notice the denominator is solvent. So up when we were looking at molarity, remember that it's moles of solute per liter of solution, solution being solute plus solvent, but parts per million is solute per solvent. Okay, so just that denominator is slightly different. It's not solution, it's just the solvent in this case. Okay, all right, and then perhaps the more common thing that we do is molarity by dilution. Okay, so let's say I've got this solution that I made in my stockroom and I need to dilute it down to a new concentration. Now I'm going to tell you, you can never make a solution more concentrated. You can only make it more dilute. And this is what you would be doing if we did this lab. So molarity by dilution uses this. M1V1 equals M2V2. Molarity 1, volume 1 of your stock is equal to molarity 2, volume 2 of your desired solution. So in other words, let's put it this way. Let's think of it like this. I'm going to see if I can draw this. There, this would represent my stock. And I use this all the time, this equation all the time. So the M1V1 would refer to my stock, and then the M2V2 this would be my desired solution. So my stock solution, my desired solution. So let's see here. Mrs. Nielsen needs to make 500 mils of a 2 molar hydrochloric acid solution for her students to use in lab. So I go back into my stock room and the only concentration of hydrochloric acid that I find back there is 18 molar. Now 18 molar is extremely concentrated. I would never give you all 18 molar hydrochloric acid, but we always buy the most concentrated acid we can because we can always make it more dilute by adding water. You can't make a solution more concentrated. You never add more solute to it. You just dilute it down by adding more water and make it less concentrated. If I needed a more concentrated solution, I would have to start from scratch. And I'll show you guys how to do that in just a moment, okay? So I need 500 mils of a 2 molar hydrochloric acid. I go back into my stock room. I find this 18 molar hydrochloric acid, and I've got to dilute it down. So how much stock acid will she use to make the solution? Okay, so I'm going to just go ahead and plug and chug into M1B1 equals M2B2. So I know that I've got an 18 molar stock solution. I want to know what's the volume that I need. Right? That's what I'm solving for. And I need a 2 molar solution. That's my desired concentration. Molar. I'm not even going to put in my units here because otherwise it gets a little too confusing. It's easier to see what the unknown is if I don't include units. So, and I need 500 mils of it. And it doesn't matter what your units of volume are as long as it's both the same on both sides of the equal sign. So I can keep this as 500 mils or I can turn it into 0.5 liters. It doesn't really matter. But if I put in milliliters on this side of the equation, then my volume is going to come out in milliliters here. So it's pretty simple, right? You just plug and chug again, divide both sides, multiply both sides. I'm sorry, multiply the 2 times 500, divide it by 18. And we should end up with a volume of 55.56 milliliters. So in other words, I'm going to go ahead and measure out 55.56 milliliters of that really concentrated stock solution. This 18 molar stock is so concentrated that as soon as I take the lid off of it, it would start smoking. I would definitely need goggles, an apron, and gloves. I would do this in the hood because that stuff is gnarly concentrated. That's the most concentrated hydrochloric acid I've ever seen is 18 molar. I don't even think we have that at school, actually. I think we only have 12 molar, but 18 is really, really concentrated. Anyway, so I'd go measure 55.56 mils of this stock solution, and then I'd go get a 500 milliliter volumetric flask. And I'll show you guys what a volumetric flask looks like in just a moment. Oh, let me clear this out. So it says, how much water will she add to dilute the stock solution to the proper concentration? So think of it this way. If I have, how am I going to do this? Let's try this. Okay. Let's say here's my container, right? Let's pretend it's my 500 milliliter flask. What I'm going to do is measure out let's see if I can get this to work. This is going to be 55.56 liters of that acid, of that 18 molar hydrochloric acid. Really, really concentrated stuff. And then I'm going to fill it the rest of the way with water. So let's see if I got another color here. So the rest of this is going to have to, oh, that's not what I meant to do. Oh man, I'm screwing this up. Oh well, okay, let's see here. So this 55.56 mils. Oh. I'm really trying to use color here to make this easier to see, but I'm struggling. Let's try this again. So here is my acid. Okay, all of this is just that really, really super duper strong stock. And then I'm gonna come over here and I'm gonna fill it the rest of the way with water. So all of this is gonna be water. Now I wanna know how much water am I gonna add, okay? Well, the amount of water that I add is just gonna be the difference, right? I need 500 mils of solution in all. So if I have 500 mils of solution in all, and 55.56 of it is stock solution, right? Then if I just subtract the two, I end up with 444.44, not a nice number, milliliters of, and so essentially I take this much acid and this much water, and now I've diluted it to the perfect concentration for you all to use in the lab. Okay, so essentially you just fill it up to 500 here. Okay, all right, and that's pretty much it. Okay, that's what I wanted to share with you guys today. These are the 3 different ways of measuring concentration that you all should be familiar with. So molarity, moles of solute per liter of solution, parts per million is milligrams of solute per liter of water. And then molarity by dilution just means when you have this solution already made, how do you dilute it down to a new desired concentration? Okay. All right, now we still have 15 minutes, which is perfect timing. Let's see here. I want to show you, in just a minute, I want to show you what some of this glassware looks like. I want to say that I have an image somewhere. Give me just a moment. There it is. Exactly what I want. Okay, good. I'm so glad I found that so easily. Okay, I'm going to share my screen again, and I'm just going to show you some pictures of what this looks like in reality. So, okay, so how to prepare and dilute a stock solution made to the correct concentrations. So if I wanted to make a 1 molar sodium chloride solution, I'm not going to go measure 1 mole of sodium chloride, right? I don't have time to sit around and count out 6.02 times 10 to the 23rd sodium chlorides. I'm going to figure out how much mass it is because I can easily weigh that with a scale, right? So I'll go get 58.44 grams of salt, and I'll put it into this cool type of glassware. This is my favorite kind of glassware. It's called a volumetric flask. And the volumetric flask is the best for making solutions. There's only 1 line on it. It's only for a particular volume. There's only 1 line on the volumetric flask, and it's super duper precise and accurate for that particular measurement. So I'd go get a liter volumetric flask. I'd put 58.44 grams of salt in it, and then you fill it with your distilled water all the way to the line, shake it up, and bam, you've got this 1 molar sodium chloride solution. Okay, and that's it. Okay, this is what it would look like. And then if I wanted to dilute that solution, like let's say I wanted to take that 1 molar solution and dilute it down, I just measure out the volume that I need and put it into a new volumetric flask and fill it the rest of the way with water. Okay, so I kind of wanted to show this to you in the lab. Let's see. Yeah, let's see if I can kind of show you what this looks like. I have some equipment here that I wanted to attempt to show you what this looks like today. So if we were in lab, and this is what I'm going to have you guys doing tomorrow. Okay, I've got my little wannabe lab set up. What you would do is take, you'd figure out some mass of salt, and you're going to do this for me. I would have you guys making a solution with salt as your solute. So I would measure out on my balance some certain amount of salt, right? So, okay, and you're gonna calculate how much salt that you need in the lab tomorrow. Okay, so you would weigh that out, and I can put it into grams here. This is 15 grams of salt. Oops, shame on me, I didn't zero my balance here. Let's do that again. Of course, I would zero my balance first, and then I would pour my salt in and measure out the appropriate amount of salt that I want, right? And then I would take this, imagine this is a volumetric flask, right? Pretend this is my, I don't know, some 100 milliliter volumetric flask is what I would normally have you guys working with here. So then you would take the salt that you measured and you would make a solution out of it. Okay, and you'd mix it all up. Okay, let's say that you filled it all the way to the line on your volumetric flask, and then you stir it up. This isn't really a scoopula or a stir, but this will work. It's here, okay? And then I would have you guys come up to the front and I would say to you, okay, you give me your solution in your volumetric flask. Okay, I'm sorry, I don't have a volumetric flask, but I do happen to have a beaker. So you bring me your solution to the front of the classroom on lab day. And I would say, okay, how did you make it? And you would tell me, I put this much salt in there, and I would verify that it goes all the way up to the line. And then I would do this. I would say, okay, then I would put a little bit of food coloring in there. And I'd mix it up and I'd say, okay, now this is your stock solution. Okay, I want you to take it now. So let's see, this is your stock. Okay, so now pretend that that's your stock solution that's in the back room. And I say, I want you to go dilute that down now, okay? And so you go, I say, I want you to dilute it to this new concentration. And so you'd go out and you'd get another volumetric flask. You would use M1V1 equals M2V2 to figure out what volume of stock solution you need to make this new concentration. You measure it out, okay? And let's say, you know, you decide, okay, it's 50 mils of this new solution. Okay. You measure out exactly 50 mils of your stock, and then let's say I want 200 mils of that new desired solution. Okay, fill it up. And then if you compare the two, the kind of fun thing is that it's not super obvious on the screen, but it's really easy to see which one's more concentrated and which one's more dilute, right? Obviously the stock is more concentrated, and then your newer solution is more dilute. Okay, so that's essentially what the lab is that you guys are going to be doing tomorrow. You don't have to do it in your kitchen. You could. You probably have these materials in your kitchen, but you don't need to. You don't have your volumetric flasks. So, but that's essentially what you do, and it makes it pretty obvious which one is more concentrated and which one is more dilute because of the food coloring, okay? So what I'd like to do for the last 10 minutes of class here before we leave today is I just wanna go through the pre-lab with you, just to make sure that you know what kind of calculations you'll be doing for that lab tomorrow. And then you're gonna submit all this on Google Classroom, and you guys have been really good about doing that, so thank you so much. So let's go ahead and find that lab. I'm gonna share my screen again. Where is it, where is it? Here we go. Okay, so this worksheet you should be able to do tonight, and then this preparing solutions and dilutions lab would be like our classwork for tomorrow, okay? So if you pull this up, I just wanna go through the pre-lab with you. Okay, so preparing solutions and dilutions, you've got molarity is moles per liter, percent by mass of solute is just a percentage. It's a part to whole ratio, mass of solute divided by mass of solution times 100. And then you'll be using this molarity by dilution equation where you're gonna dilute that stock solution down to a new concentration, okay? So your objectives, 2 skills that are essential for a chemist are preparing solutions of known molarity and diluting those solutions to a new molarity that's less concentrated. As a basis for understanding the concept, the goal is for you to accurately prepare a stock solution, like I did here for you, and then to dilute it down to a new concentration. okay? That's less concentrated to a new desired molarity. And so these would be your materials that I would give you, these cute little volumetric flasks that are only 100 mils. And remember, a volumetric flask only has one line on it. It only has one line that's really, really accurate. So it would be for this one, 100 milliliter. I have volumetric flasks of all different volumes. I have 100 milliliter ones that we use for this lab. We have 500 milliliter ones. We have 1 liter. We have 2 liter volumetric flasks. So you just grab the size based on how much solution you need. You get a funnel, you get a balance. Your sodium chloride, we would just be using tap water. You'd need a graduated cylinder, a dropper, and then a small beaker as well. Okay, so let's just go through these pre-labs. First one says differentiate between the terms solute and solvent. Okay, hopefully you guys can do this by now, but solute is the substance being dissolved. And then solvent, let's try this over here, is the substance that's doing the dissolving. Usually it's water that is the solvent, right? Almost always it's water, unless it's otherwise stated that it's something else. So don't forget solute is the smaller word, so it's usually the substance that's in lesser quantity, and the solvent is the bigger word, and that's the substance that's in the greater quantity. Okay, so there we have our two definitions. Next one, how many grams of silver nitrate are necessary to make 1 liter of a 6 molar stock solution? Okay, so here I've got my equation. Molarity is moles per liter, right? So start over there. Molarity equals moles of, in this case, it's going to be silver nitrate per liter of solution. So I've got my 1 liter or 6 molar, and I want 1 liter of it. So I can say that 0 is equal to some X number of moles divided by, and then we should be able to solve for X. It's going to equal 6 moles, right? Silver nitrate. And that's pretty easy. But again, I can't go and just measure 6 moles. That'll take me forever to count 6 moles, right? I'm gonna have to use mass to do it. So I'm gonna go get my balance, and I'll get my little silver nitrate bottle and my scupula and my weigh boat, right? And I'll figure out the mass of this. So I'm actually running out of space here. So I'm gonna use my board instead to work through this one. Maybe it'll be easier for you to see that way. So if I have to measure out 6 moles of silver nitrate, I got to figure out the mass of that. So convert to grams. And the molar mass of silver nitrate, 1 silver, 1 nitrogen, 3 oxygens, its molar mass is 169.88 grams. Moles cancel, and this measures out to 1,019.28 grams of silver nitrate. Now, you might be tempted to round to 2 sig figs, but because I want to make my solution as accurate as possible, I wouldn't recommend rounding to sig figs when you're making solutions, okay? Just because otherwise it gets less accurate, right? You want to get as many, the exact amount of solute that the calculation says you should get. Don't round it. And I have balances that go to 2 decimal places. So I would go over to my balance and I'd measure out this much silver nitrate. And then I would go get a 1 liter volumetric flask. And I would put, I'd take this. Here's my little volumetric flask. And I would have, it would be 1,000 milliliters would be the one marking on it, right? That would be my 1 liter volumetric flask. And I'd go in and put this many grams of silver nitrate in there, and then I'd fill it all the way to the top with water, and bam, I've got my stock solution, okay? The next question on this pre-lab, last one, says, how would you make 1 liter of a 0.1 molar solution from my 6 molar stock solutions? So now I would label this stock solution here. I'd say, okay, here's my 6.0 molar silver nitrate solution, right? And I would initial it and I would date it for 2020, right? But now this is my stock solution. I want to take this stock solution and dilute it down to a new concentration that's 0.1 molar, okay? So how am I going to do that? All right, I'm going to use that molarity by dilution equation. We're almost done here. So I'll use M1V1 equals M2V2. Okay, and remember this represents my stock, and this represents my desired solution. Okay, so I just made my 6 molar stock solution. Better pen. And I want to know what volume of it do I need, right? That's my unknown. In order to make 0.1 molar solution, and I want to make 1 liter of a 0.1 molar solution, right? So this is my molarity, and there's my volume, 1 liter. And so when you multiply and divide, you end up with this volume of stock is 0.017 liters, which is the same thing as 17 milliliters, right? So I'm going to go take that stock solution I just made of silver nitrate, the 6 molar silver nitrate, and I'm going to go measure 17 milliliters of it. I'm going to get 17 milliliters of it, and I'm going to put 17 milliliters. Right, there's my little 17 mils of that 6.0 molar silver nitrate stock solution. Okay. And then this is a 1 liter volumetric flask, right? So there's 1,000 milliliters, right? Because that's how the volume that I need. Okay? And I'm going to fill the rest of the way with water. So all the rest of that is going to be water, right? And so how much water are you going to add? Well, it's just going to be the difference between the two. So if I say, well, the total volume is going to be 1,000 milliliters when I'm all done, and 17 milliliters of it is my stock solution, then that means 983 milliliters is water. Right. Okay, and so to make that stock solution, I just go measure 17 mils of that stock that I just made, fill it up to the line with water, and now I just diluted it to this new concentration that's 0.1 molar, and I have a whole liter of it, right? And so that's it. That's how we make solutions in lab. I hope that was helpful. Again, I really wish we could be together in class so that I could teach you how to do this with our proper lab equipment. But I hope that you have a better idea of how to make solutions now after watching this. All right, so that's it. I'm going to go ahead and stop recording now. And if you have any questions, you're free to stick around. Thanks for coming. Have a nice day.